Okay, YouTube, in this video I'll provide a basic overview of how you add and subtract rational expressions involving variable expressions. We're going to start up here on the top left, and we're going to talk about the basic premise of adding and subtracting fractions in the first place. That being that you have to have a common denominator between your two rational values, okay? So in either instance here, you'll see that I have like 4 over 3x plus 5 over 3x, or these are both over the factor x plus 3, but the idea is that if these are the same, then really what we're operating on is not the denominator, okay? So we would never say that this is 2 times x plus 3, because we wouldn't just add the denominators together. We would say that what it's equal to is instead x plus 3 on the bottom. We still have x plus 3ths. It's just that how many do we have, and we would just operate with the numbers on the top. So we would say then I have 2x minus 4 of those, okay? And as a matter of fact, because the top can be factored, we probably should do that. We say 2 times x minus 2, but nothing cancels out top and bottom. But we would say here's the simplest form, difference here that you see on the left there, okay? And we say that over here we would just get, over 3x. We'd say they have a common denominator, 3x. It'll be 4 plus 5 on top. And so in other words, we get 9 over 3x, and this would be an important instance here where we would actually want to make sure that we wrote this in simplest form, and I noticed that the top and bottom shared a common factor of 3. So anyways, moving on, we say, well, with strictly numerical values, what if you don't have a common denominator? How is it that we actually obtain one? And so I would actually argue that 12 would be actually what we call the least common denominator between these two here. So we would say that LCD is equal to 12. And to define what the LCD is, what it's really equal to is the LCM of the denominators. That is to say, if we were to write out multiples of 6, we would say that we would have 6, 12, 18, 24, and so on. And then those are all factors of 6. We say these are all factors of, or 12 is a factor of all of these, rather. But essentially, we say that the least common multiple they have in common is 12. Well, one thing I do want to point out is that if we were to just take 6 times 12 and 12 times 6, if I said, let's do this. Let's take this fraction on the left times 12 and this one times 6. But we'd have to do the same thing to the top that we did to the bottom. What you start to see is this thing that would work. It would totally work. 72 would be a great common denominator. It's just that it wouldn't be the least common denominator. So often what we're after is what is the smallest denominator that these two things have in common, and that's what we're going to try to pursue here in this video. So in terms of a technique like how you might do that, what I would have argued that we do when we have algebraic expressions is that we tend to try to factor everything on top and bottom as much as possible. So the very first thing we would do is factor every expression we possibly could. And so we would get 1 over, and I would say this is 2 to the first times 3 to the first, plus 5 over, and we notice here that if I were to say, what's 12? It's 4 times 3. I'd say this is 2 to the second times 3 to the first. We notice that this one over here has an additional 2 built in. So what we often do mentally, is say, well, we'll just take this times 2 top and bottom. What we would do mentally is we would do algebraically this way. We would say, well, I need another 2 over here in this expression, top and bottom, because that's the rules. I got to multiply by 1. But essentially, if I could build in one more thing that this needed over here, this 2, then these two denominators would be least common denominators. I could say that now everything is over 2 times 3, everything. And what we get is really 2 times 1 plus 5. 2 times 1 plus 5 on top. So this is what we're going to be doing here in these expressions. We're going to take a look at this very first one down here. We said that we have a 5 over 6x squared plus an x over 4x squared minus 12x. Now, first thing I notice is that this is, it's got a greatest common factor. So I'm going to rewrite this as 5 plus, and I'm going to write an x over here. You notice that I didn't write this denominator over here yet. I'm going to leave that out for just a moment. But I'm going to say that I would factor out a 4 and an x from both of these terms here, and it would leave behind an x, and I would think it's x minus 3. So now I'd say, well, what do these two denominators have in common? Well, first of all, the one on the right has a 4, an x, and an x minus 3. So it has 3 factors here. This one over here, you would say, well, how many factors does it have? Right now, you would say, really, technically 2, because the 6 and the x squared. But what I want everybody to notice is that this is really a 6 times x times x. So when we talk about, well, what could we load both these denominators up with? Like I can't take any of these out, but I could, give each denominator what it would need to kind of catch up with the other one. And the other thing here is, I guess I would even note this. We would say that the 6 is 2 times 3 times x, whereas over here 2 times 2 times x minus 3. But basically what I notice is that both of these denominators have a 2. They both have an x, they have this x here. It's just that this one over here has a 3 and an x, where this one needs an additional 3 and an additional x. And over here, this one has a 2 and an x minus 3, where this one needs a 2 and an x minus 3. So we're going to take this times 2 times x minus 3. And I'm going to try to squeeze this in here, but essentially what we would do, and maybe I'll do this here, is after we've kind of diagnosed what each of these needs, we're going to say this really, we're going to say that I would have to take this one on the left, top and bottom, times x minus 3 times 2. So we're going to take the top here, 5 times 2 times x minus 3. And this is all over now 6x squared, which is what we had initially, times 2 times x minus 3. And this is all plus now. Now this on the right here, we would say x, we had to take it times a 3 and an x. So we'd take it times another 3 and another x on top and bottom. Now it already had a 4x, x minus 3. But if we take that times another 3x, what I want everybody to know is that these two denominators here, if we simplify them, are going to be identical. Okay, so I do want to actually simplify these, and I notice that I get 6 times this 2 here is 12, the same thing as this 4 times this 3. X times x is the same as this x squared here, so 12x squared, and then x minus 3 would be our least common denominator. And then on top, what we would get is, we'll start simplifying this here, we get 10 times x minus 3, all of this on the left here, basically, plus all of this on the right here. So we say plus now x times 3x, which is 3x squared. So we're just going to work on simplifying this here. I basically mean the top. We want to go ahead and expand this, combine like terms, and factor if we can. So that being said, we'll go ahead and say, well, we get 10x minus 30 after distributing our 10 plus 3x squared. So all over 12x squared, x minus 3. I'm going to invade some space here, but I noticed at the top here, you know, if we were to put this in standard form, I could take out a 3 also. We could say 3x squared. And, oh, no, 3 is not a factor of 10, so we can't take that out, but I can certainly put 3x squared plus 10x minus 30 on top here. And I could say this is all over 12x squared, x minus 3. So now I'm going to say with you know, a certain degree of confidence, I don't think that the top here is factorable, and we should check it to see if it simplifies, but basically that's going to be our method for finding common denominators between things. Okay, so let's make this a little bit quicker on these last two examples. Step number 1 is going to be this: if unlike denominators, factor each completely. This is so important. Factor everything completely, and then we'll find, you know, a common denominator. And if they already have common denominators, we're just going to skip down straight down to add and subtract the numerators and place over the least common denominator. But if they don't have common denominators, basically step 2 here is going to say, look, what you need to do is you need to get one. So looking at these here, I'm going to rewrite this. I'm going to try to keep my handwriting a little smaller this time. I notice that this is a trinomial. A is 1, so can we think of two numbers that multiply out to be a negative 4 that add up to be a positive 4 here? You know, I can't think of any. It would be negative 4, positive 1, positive 4, negative 1. What I'm going to do is I'm going to actually temporarily switch this to a positive, because then I could think, you know, this would factor into an x plus 2 situation. Okay, I think I like that better. And we'd say that this over here, this is a difference of squares, so it's going to factor in conjugate pairs, where we have x squared, x times x would be x squared, and 2 times 2 would be the 4. So we would say that noticing both of these already, they both already have an x plus 2. What does this one need that this one has, and what does this one have need that this one has? Basically, on top and bottom here, we're going to have to build in an additional factor. This one over here needs an x plus 2 over x plus 2, and over here, this one's going to need an x minus 2 over an x minus 2. So what we end up with here is this: we get x minus 2, x plus 1, minus 2 times x plus 2. And this is now all over. And the way I'm going to write this here is x minus 2 times x plus 2 squared, because we had 2 of these x plus 2 squared factors, and this is a little bit more convenient to leave it factored. So in most cases, what we would do is we would simplify the top here. Let's go ahead and do that. We'd say that this becomes x squared plus x minus 2x is minus 1x. And then we say minus 2. And this is all minus 2x minus 4. Okay, so if we were to combine like terms now, I noticed that on the top, we would get, let's see here, we get an x squared. We get negative x, and negative 2x is negative 3x. And our constants here, negative 2 and negative 4, give us a negative 6. So can I think of two factors of negative 6 that would multiply out to, or add up to be a negative 3? You know, 3 and 2 don't work, and 1 and 6 don't work here. So I would say that the simplest form of this here, we would say that I can't cancel out any factors from the top and the bottom in common. We'd say that is this right here, and that was our difference this time. So this very last example I want to look at just basically points out a basic premise that we always kind of assume, is that if you were to take a fraction plus a whole value, you put that whole value over 1. And the very nice thing about this is we say, well, over here, I try to factor the top and bottom, but I can't factor anything else out. And I noticed that the least common denominator would be the you know, the product of these two things here, or at least this over here would need a d minus 4. D minus 4. And this one over here we could take times 1 on top and bottom. But essentially what we're going to get is this now all over the common denominator, which is 1 times d minus 4. I'll even write that out. We would get over here 1 times 2d minus 1 is 2d minus 1. That, and now we're adding plus 2 times d minus 4. So again, we're going to simplify the top and the bottom here. We get all over d minus 4 now. And we get 2d minus 1 plus 2d minus 8. And combining like terms here, it looks like 2d and 2d is 4d. And we get negative 1 and negative 8 there is negative 9. So I can't factor that. So nothing's going to cancel out top and bottom, but bottom line is this is going to be our sum right here, and that's how we found its common denominator. Cheers.